Hello. In this video, we're going to continue with Chapter 17. In a previous video, we looked at solving equilibrium calculations, and we specifically focused on situations where the system was already at equilibrium, and we were trying to find missing information equilibrium, either an equilibrium concentration or maybe the K value for that particular reaction. But now we want to look at a scenario where we must determine all of the concentrations at equilibrium. And we're going to do that with something known as an ice table. And so the easiest way to kind of present this is to just do a problem, okay? So let's say we have the following reaction, 2HI, gaseous, in equilibrium, forms H2 gas plus I2 gas. Move it down a little bit, okay? And so let's say we're told that a 2.0 liter flask is filled with 0.200 moles of hydrogen iodide gas and allowed to react at a temperature of 453 degrees Celsius. Okay? Now, in this problem, we're not going to determine all of the equilibrium concentrations, okay? But we are told that at equilibrium, the concentration of HI is 0.078 moles per liter. And what we want to know is, what is K at 453 degrees Celsius? Okay, and so this is where we are going to implement an ice table. Let me move this over here a little bit because we're going to use that diagram in a moment here. So what is an ice table? An ice table, so I C E. So I stands for the initial concentrations, C stands for the change in concentration, and E stands for the equilibrium concentrations. So ICE. And so the way that this table works, okay, is that the sum of the initial row and the change row, either in this case in terms of concentration, but you can do ice tables with pressures as well, will equal what the equilibrium and what the equilibrium concentrations or pressures are. So first off, we need our initial concentration, and we're told that a 2.00 liter flask is filled with 0.200 moles of HI gas. It's the only gas we put in and then allowed to react. So first off, we have to calculate what our initial concentration of HI is. And like we've done in a previous problem for gases, we just take our moles of the gas divided by the volume in liters of the vessel it's in. And if we do that, 0.200 divided by 2.00, we get 0.100 moles per liter. Okay, so we know that our initial concentration of HI, so we're in the initial row here, is equal to 0.100 moles per liter. Now, by reading the question, we can see we have added 0 moles per liter of H2 and 0 moles per liter of I2. Okay? 0 moles per liter of H2, 0 moles per liter of I2. So we're starting with none of those. So to figure out what to do with the change row, we need to figure out, is Q less than K or is Q greater than K? In other words, what side of the equilibrium are we on? Okay, we're not at equilibrium. So we first need to, using our initial conditions, calculate Q. And so we've already done Q expressions, so I'll just do this very quickly. So we have our H2 concentration to the first power, which is 0, our I2 concentration to the first power, which is 0, and then our HI concentration, which is 0.100 to the second power. And we can immediately see that Q is equal to 0. So we are starting at Q equals 0. This is where we're starting. So note, to get to equilibrium, down here, okay, so first of all, note Q is less than K. But what does that mean that Q is less than K? Well, note we have to proceed to the right to get to equilibrium because Q is too small. Q needs to increase. And so what that means is our concentration of reactants need to decrease and our concentration of any products must increase. Okay? So decrease in this case means a minus sign, and increase in this case means a plus sign. So if we go over here, we know these are going to change by some number X in concentration, right? So the change in concentration is our X, right? That's how we're getting from Q equals 0 to Q equals K. Okay. And and we don't know what K is yet, but we know that 0 is lower than K because K cannot be negative. So it has to be greater and it can't be 0. So we know Q is less than K because 0 is less than all positive numbers. Okay. So first thing to note is these are going to change by some amount and it's based on their coefficients. Okay. So to get to equilibrium, the change in HI is going to be twice the change in the H2 and I2 concentrations to reach equilibrium because we have to follow stoichiometry. We talked about that in chapter 16 with kinetics. But what we're determining from Q is less than K is that our reactant concentrations must go down, so minus sign, and our product concentrations must go up to reach equilibrium. So that's what Q less than K is telling us. Reactant changes are subtractions and product changes are additions. If we had instead been on the right side of the equilibrium, like Q equals infinity, right, which occurs when you have non-zero values for all of the products and a 0 value for one or more of the reactants, then Q would be greater than K. Even though we don't know K, we would know that infinity is greater than whatever K is, because K is a number between 0 and infinity. And so then things would be reversed. Then we'd have a positive sign for any reactants because they need to go up in concentration, and we have a negative sign for the change in our products. Okay. But again, in this case, we have negative for the reactants and then plus and plus for the products. And again, remember the coefficients multiply by the X. So that means our equilibrium concentrations are as follows. Our equilibrium HI concentration is 0.100 minus 2x. That is our concentration of HI at equilibrium, right? Our concentration of H2 at equilibrium is 0 plus x, which is simply x. So that is our H2 concentration at equilibrium. And then the same thing for I2. 0 plus x is just x. Okay. Now, we want to determine Kc, and to do that, we need to know our equilibrium H2 concentration, our equilibrium I2 concentration, and our equilibrium HI concentration squared. So how do we determine this, right? Because we don't know K and we don't know X. We don't know our equilibrium concentrations. However, we were given another very important piece of information. We were told this, that at equilibrium, the HI concentration is 0.078 moles per liter. Let me move this over here. So what that means is that our algebraic expression of 0.100 minus 2x, which is the HI, the hydrogen iodide concentration equilibrium, is equal to 0.078. This allows us to solve for x. Okay, this allows us to solve for x. So we take 0.078 minus 0.1, divide, and then we take that divided by -2, and we get that x is 0.011. So that means these equilibrium concentrations, which are just x, are 0.011 and 0.011. So now we have all of our concentrations. We could plug in our 0.011 concentration for our equilibrium H2 concentration, 0.011 concentration for equilibrium I2 concentration, and then 0.078. And remember, we're going to square that. Do not forget your coefficients become powers, right? So coefficients show up in the change row there, as well as in the powers. Very, very, very common mistake. So if we continue with this calculation, 0.011 times 0.011 divided by 0.078, because that was given to us, but we also used it to calculate x, which was the concentration of H2 and I2 at equilibrium. Okay. And we get a final answer in scientific notation to 2 significant digits. So we started with 3 significant digits. And then when we did our subtraction, we needed 3 decimal places. So 0.011 is 3 decimal places. But when we plug that in, that ends up being 2 sig figs when we follow that addition subtraction step up with multiplication division. And so our final answer is 2.0 times 10 to the -2nd, which is, again, we were told, at 453 degrees Celsius. There's our final answer. Okay? So that is one way to approach a problem like this. Let's look at a different type of problem. Oops. Let's bring this all the way down here. All right. Let's continue. Okay. So same deal. Okay. We are going to use the following reaction: CO2 gas plus carbon solid in equilibrium with 2CO gas. There's our reaction. We want to know what Kp is this time at some temperature T. Okay. And what we're given is that our initial pressure of carbon dioxide is 0.458 atmospheres. Okay. We were not given our initial pressure of CO. So that means our initial pressure of CO would be 0 atmospheres. Okay. Now, the other piece of information we are told, so these are our initial pressures. We're also told that the pressure total of the system at equilibrium is equal to 0.757 atmospheres. Okay. Note total. Okay. So we'll come back to that in a moment. So first off, let's go ahead and set up our ICE table here. Okay. We want to know what Kp is. So we're going to be dealing with pressures rather than concentrations here. But first, we need to know what Q is. Right? And then we determine, is Q greater than or less than K? And then so on, right? And then equilibrium Q equals K. All right. So our initial pressure of the CO2 we were given, that's 0.458 atmospheres. Now, carbon is a solid. Solids do not show up in K expressions. So we're just going to block those out because we don't need values for that, because our K expression does not include the pressure for the solid carbon. Okay. Our initial pressure of carbon monoxide is 0 atmospheres. And so if we set up that equilibrium expression, that Q expression, it's going to be the pressure of CO, the initial pressure of CO, which is 0, which is 0 squared. And then our initial pressure of CO2, which is 0.458 to the first power. And note that that equals 0 again. So again, we're starting here. Which means that Q is less than K, and thus our reactant concentrations got to go down, and our product concentrations got to go up. Right? We need to make Q bigger. Q is currently 0, and it's going to increase until it reaches Kp. Now, since we now know that Q is less than K, that means we have a minus sign here and a plus sign here. We already know that this is going to be X here and 2X here, because again, remember, our coefficients determine the coefficient of our change X, and Q determines the sign of our change, plus or minus. If one side is plus, the other side has to be minus. So note, Q is less than K. Reactants are minuses. Actually, I'll block this out more, right? We're ignoring that column. Okay. Reactants are minuses. Products are pluses when Q is less than K. When Q is greater than K, reactant changes are pluses and product changes are minuses. So then our equilibrium, once we reach equilibrium, when Q equals K, our pressure for our CO2 at equilibrium will be 0.458 atmospheres minus X. So that is our pressure of CO2 at equilibrium. And our equilibrium pressure of CO is going to be 0 plus 2X, or simply 2X. So that is our pressure of CO at equilibrium. So again, we can set up our expression here. So we know that our Kp expression is going to be our equilibrium concentration of CO squared over, sorry, not concentration pressure, our equilibrium pressure of CO squared, our product, over our equilibrium pressure of CO2 to the first power. Let me clean things up here a bit. So again, we have two unknowns. We don't know K and we don't know P. So we need to figure out what X is. So again, we need to be given more information, and we are given this information, that the total pressure at equilibrium of the system is 0.757 atmospheres. So what do we mean by that? Well, Dalton's law of partial pressures says that the total pressure for this system is going to be equal to, at equilibrium, is going to be equal to the pressure of CO2 plus the pressure of our CO, right? And we know that that is 0.757 atmospheres. We know that the pressure of CO2 is 0.5458 minus X, plus we know the pressure of the CO at equilibrium is 2X. Okay? So we end up with the following problem that allows us to evaluate for X. So 0.757 equals 0.458 plus X, because we have a 2X plus a negative 1X. So we have just X. Therefore, X is going to equal 0.757 minus 0.458. So 0.757 minus 0.458. We get a value of 0.299 for X. Okay. Note 3 decimal places because we're doing addition and subtraction in that last step. But that also is going to be the number of sig figs when we go to calculate this at the end. So now, if we take this and plug this back in up here for each of these, let me move this expression down here. Okay. Then we are going to get 0.458 minus 0.299 for the equilibrium pressure of CO2. So we get 0.159 atmospheres. And the equilibrium pressure for CO is 2 times X. So 2 times 0.299. And so that is 0.598 atmospheres. Note, if we add those together, we should get our 0.757 back, and we do indeed. So now we're going to plug these values in. Okay, so we're going to have 0.598 to the to the second power, sorry, divided by 0.159 to the first power. Again, note your coefficients of your chemical reaction show up both in the change row as the coefficients of the change and in your equilibrium expression. So don't forget that. So 0.4598 squared divided by 0.159, we get a final answer of 2.25 as our equilibrium constant using pressures for this calculation. So that is just some calculations so far. Okay. We've done some calculations so far. So let's go ahead and we're going to move on to a different, more complicated scenario, slightly more complicated. It's going to involve perhaps some math that you haven't seen in a while. Okay. So we don't need the curve anymore because I think we understand now what we're doing. So let's say we are given that our initial conditions are that we have some reaction, carbon monoxide plus H2O gas in equilibrium with CO2 gas and H2 gas. And we're given our initial conditions are our moles of CO, 0.250, our moles of O2, or sorry, H2O, 0.125 moles, and the volume of our flask is 125 mils. Okay, so note our moles of CO2 and our moles of H2 are 0. We were not given that information, therefore we must assume that there is none. Okay, so we're going to build our ice table here, and what we want to know for this is we're given Kc, which is 1.56 at a temperature of 900 Kelvin, and we want to know what are the equilibrium concentrations, right? What are the equilibrium concentrations? So let's go ahead and evaluate this. So I need to know my concentrations of CO, H2O, and CO2, and H2, sorry, under for our initial conditions. And so for our CO2, it's 0 moles per liter, and our H2, it's 0 moles per liter. For our CO, it's going to be 0.250 divided by 0.125 because 125 mils is 0.125 liters. And so we get 2, but we got to maintain sig fig, so 2.00 moles per liter. And then our concentration, our concentration for H2O is 0.125 divided by 0.125, and that is 1.00 moles per liter. Okay, now we calculate, we know our change is going to be X, 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 and X. A bunch of ones, so they're just all X's. We're going to calculate Q real quick, so it's going to be 0 times 0 over 2.00 times 1.00, and thus Q equals 0, and so Q is less than K. And so remember, Q is less than K means that our reactants are going to go down in concentration, and our products are going to go up in concentration to reach equilibrium. So that means that our equilibrium concentration of CO is 2.00 minus X. Our equilibrium concentration of H2O is 1.00 minus X. Our equilibrium concentration of CO2 is simply X. And our equilibrium concentration of H2 is simply X. Okay? And so our Kc expression here is going to be our concentration of CO2 at equilibrium times our concentration of H2 at equilibrium over our concentration of CO at equilibrium and our concentration of H2O at equilibrium. So that ends up being 1.56 equals, and now we were not given any additional information about, we weren't given any information about any concentrations at equilibrium when Q equals K. So we're just going to plug our equilibrium concentrations in terms of X into our K expression. And so we end up with the following scenario. How do we solve for X here? Well, if we try to evaluate for X, which we're going to do right now, so we get 1.56 equals X squared. And then on the bottom, remember your FOIL method, right? So first, that's 2 times 1, which would be 2.00. Outside, so that's 2 times negative X, which is minus 2.00X. Inside, that's 1 times negative X. So we end up with minus 1.00X. I'll go ahead and write the 1.00. And then last, the L. That's negative X times negative X, so it's positive X squared. Okay, so you can already see what is forming here a quadratic. Okay, so we continue evaluating. We're going to run a 1.56. We're going to multiply that expression on the bottom into both sides to cancel on the right side and move it to the left side. Okay, and so we're going to end up with, and also note that this is just minus 3.00x. So we run that 1.56 through, and so we end up with 3.12 minus 3 times 1.56, which is 4.68x, and then plus 1.56x squared, and that is all equal to x squared. And so then if we rearrange this, we're going to subtract x squared, 1x squared from both sides. We end up with 0.56x squared minus 4.68x plus 3.12 equals 0. Okay? If you remember, the way we solve something like this is with something known as the quadratic equation. Okay? So the quadratic equation, if you'll remember, is that if we have some quadratic of the form ax squared plus bx plus c equals 0, then x will be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So this will give us two values for x. Why? Why is that? Well, remember, generically speaking, right? So x-axis, y-axis, quadratics are typically the formulas for parabolas, okay? And so when y is equal to 0, okay, so when y is equal to 0, then x is going to be equal to the values where the parabola intersects the x-axis, right? So we could have a parabola like this where we get one positive answer and one negative answer. Or let's say our parabola is over here, right? And we solve for those intercepts. We could have x as a big answer and x is a small answer, okay? But the point is you get two values for x. And so because we're dealing with reality, not just math, one of those x answers is not going to make sense, okay? So a equals 0.56, b equals negative 4.68, and c equals positive 3.12. And so we would plug that in. When you're doing this at home, you can just use a quadratic solver. And so for x, you get two values. If you plug this into a solver, you get 7.63 and you get 0.732 as our values for x, okay? So those are our values for x. That's what we just got by solving this expression using the quadratic equation. Well, if we look here, if we tried to plug 0.763 in here and here, what's going to happen is we're going to get a negative value, right? Because 7.63 is greater than 2 and it's greater than 1. And so we'd have a negative concentration. And there is no such thing as a negative concentration. However, if we use the 0.732 answer, we will get positive values for all of our equilibrium concentrations. Okay. And so if we do that math, we get 2.00 minus 0.732. So we get 1.27, okay, moles per liter. If we take 1.00 minus 0.732, we get 0.27 moles per liter. We got to restrict it because of decimal places. And then for these, we get 0.732 moles per liter and 0.732 moles per liter. So there are our final answers, right? Those are our concentrations of each of our species at equilibrium. Now, while using a quadratic equation is tedious and typically your instructor will allow you to use a quadratic solver programmed into your calculator, or when you're doing this at home, you can do it using a quadratic solver from online. We can double check this. So, double check. And how are we going to double check this? Well, we're going to resolve for Kc by plugging in those values. So remember, 0.732, that's the concentration of our CO2 to the first power, concentration of our H2 to the first power, over the concentration of CO to the first power, which is 1.27, and the concentration of H2O to the first power, 0.27. And so if we plug those in, 0.732 times 0.732 divided by 1.27 divided by 0.27, and we get a value of 1.756. So that proves that our equilibrium concentrations are correct. In the next video, we're going to do some more of these, but we're going to learn a shortcut. We're going to learn a set of conditions where we don't have to use the quadratic equation by making an assumption and calculating an approximation rather than the precise value of x. So that concludes this video.